All right, Chem 12. So we started looking at the Bronson-Lowry acids and bases last class. So I'll begin with a question I received from a student. Just a little bit of clarification with how the reactions of strong acids and strong bases work. So this was from page 122. So first off, a strong acid is 100%, undergoes 100% ionization. Okay, so 100% ionization means everything that you start with in an acid is going to convert to H plus or OH minus, right? So remember, H plus is the same thing as OH minus, or sorry, not same thing as H3O plus. Okay, so those are the same thing. And so when you have an acid, when we say it undergoes 100% ionization, what we're saying is whatever concentration you have originally, say of HCl or H2SO4, some type of strong acid, all that concentration will be converted to H plus or hydronium ion. Okay, so for example, if we've got this reaction here, we've got HCl plus water, and that's going to give you H3O plus and Cl minus. So remember, the H plus is the acid. So an acid by Brown-Lowry is defined as a proton donor. So it's going to give its proton to water, which in this case is acting as a base. So water is going to receive, is a proton receiver. And so then you get this reaction. And then the H3O plus, the presence of H3O plus, is an indication that you're in an acidic environment. So here, HCl and Cl minus would be a conjugate pair, and H2O and H2O plus would be a conjugate pair. Remember, a conjugate pair is two of the same thing that differ by a proton. Now, another way to look at what this means, this type of reaction here, is basically this one, and I think this was the reaction in the textbook that was bringing about some confusion. All this is saying is this H plus is the H plus you're getting from a strong acid. So that's this one right here. Because the reason why you can say that is because if this is a strong acid, all of this is going to be converted to H plus. Okay, and so here's the same water, and then here's your H3O plus. Right, so it's essentially the same reaction. It's just saying that if you're talking about a strong acid, then whatever it is you're starting with is going to be H plus. Okay, so these are basically equivalent reactions. Now, with the strong base, it's again 100% ionization. So I think I gave this type of reaction last lesson. So there's your strong base, and it's a proton receiver. So here, water is acting as an acid, a proton donator. So you can see from these two examples, water can be either acidic or basic depending on what it's reacting with, and the term for that is amphiprotic. So here, the water is going to actually donate the proton to NH2 minus, and that becomes NH3, and there's your OH minus. The presence of OH minus is an indication of base. Okay, so when we say something is a strong base, what we're saying is it's 100% ionized to OH minus. Now, the one that isn't as obvious, and I think this was sort of the question I got, was what happens in this case when you've got KOH in water. Well, this already has the OH minus in there. So basically what's going to happen is if I write this reaction with water, the water is there before and after. And simply what happens is the K plus and the OH minus are because this is going to separate in solution, it's soluble, there are the ions there. So the other way you could simply write this is KOH is going to separate to K plus and OH minus. There's your OH minus. It's contained within the KOH, and again that is the presence of basic conditions. Okay, so OH minus is what we call the strong base part of whatever it is we're looking at. Okay, so here it's not so important as to look at, in NH2 minus we can have a reaction because we have sort of an acid-base pair. Here, KOH is simply soluble in water. It already has the strong base part in it, and it's simply going to be separate and be present in solution. So continue to to ask questions with any of the material that you're looking at. So it's important because you guys are grade 12s. It's important that you stay up with all the with everything that you're doing, because hopefully, like I said, we do get back to class, but if not, you need this. You need to know this stuff for university and college, especially if you end up taking first year science and chemistry. Okay, so let's look at the equilibrium constant for ionization of water, and this kind of goes back to what we were just looking at with those questions. So it's all about hydronium and hydroxide, and there's basically a balancing act between the two. When the two are equivalent to one another, then you've got what we call a neutral solution. We'll revisit this later when we talk about pH. When you have acidic conditions, then your hydronium will exceed your hydroxide, and if it's basic, then the hydroxide will exceed the hydronium. So the self-ionization of water is this reaction here. So there's water, liquid, pure liquid, and so this is endothermic, right? So I forget what the numerical value is in terms of how many kilojoules that is. And so you separate this to H plus and OH minus. Okay, so there's your H plus, there's your OH minus. Now in this case here, and so now we'll start getting into the equilibrium. Remember, we started the course with KEQ, which was the general equilibrium constant. Then we did the solubility unit, and then we had what's called KSP. And so now we're getting into acids and bases, so there'll be some other designations. KW is the equilibrium constant of water. Okay, and so H2O is not in here because it's a pure liquid. So remember, pure liquids and solids don't go into your expression. So there's your KW expression. It's simply the products. And this has a constant, okay, 1 times 10 to the negative 14. Okay, so we basically use the fact that this is equal to 1 times 10 to the negative 14. And so if we know one of these, we can find the other one because there's your equilibrium constant, right? So here's an example where you've got HCl, 11.5 molar. So again, that's a strong acid. Because it's a strong acid, it goes through 100% ionization. So the H plus then is 11.5 molar. Okay, so notice how they're the same. So your OH minus then is just going to be KW divided by H plus. Okay, and so that's 1 to the negative 14 divided by 11.5, which is going to be 8.7 to the negative 16 molar. Okay, so that's your hydroxide. And so basically what that's saying is your hydroxide is very little, which you would expect when you're talking about a strong acid. But the key thing here is that's still there. Okay, second one here. So you've got 0.025 molar sodium hydroxide. And so, again, this is just like that KOH. Now, the thing here that's important is the mole ratio, right? Like if you had something like magnesium hydroxide, that would be MgOH2, right? And so the OH would be double. In this case, it's a 1-to-1 ratio, so the hydroxide is still 0.025. Again, you're using the same relationship, hydroxide and hydronium equal Kw. And so there's your H plus concentration. So notice that I'm doing this quite a bit. I'm mixing up H plus, H2O plus, calling it hydronium. They're all the same thing. Okay, so they're all the same thing. They're basically how we measure the presence of acid. Okay, so your hydroxide is bigger than your H plus, therefore it's basic. Okay, now that's Kw. Let's look at Ka and Kb. So Ka is Ka has to do with the weak acid. Kb has to do with the weak base. For the strong acids and strong bases, there is no equilibrium because you don't have a reversible reaction. Now let's look at something like acetic acid. this one is going to be in equilibrium. So basically what this is saying is acetic acid will, some of it will ionize to acetate ion and hydronium ion, producing some of the hydronium ion, but a lot of it will still stay in the acetic acid compound. So the weaker the acid is, the more of the original will stay as is, and the less of the hydronium ion will be produced. Okay, so the stronger it is, the more of the hydronium ion you're going to be produced, and the less of the original acid you'll have. Okay, so again, water is a pure liquid. So here's your Ka expression, and there's your Ka constant. Now you have all these values of the Ka constants are in the table at the back of the textbook. Okay, so you have a Ka table where you can get those values, and it's a constant value. Okay, just like KSP was. The only thing that will change it is temperature. Similarly, weak bases also undergo an equilibrium expression, right? So there's NO2 minus. Okay, so there's your reaction, and there's your Kb. Now the problem with the weak bases is they're not in the their values aren't tabulated like the Ka values are tabulated. So what we have to do is when we want to find the Kb value, we actually have to calculate it, and that's what the final part here is going to look at. So this is the relationship that we use. Okay, so Ka of the conjugate acid times Kb of the conjugate base equals Kw. Okay, so that's your formula there. So suppose we want to find the Kb of F minus. Okay, so there's your weak base. So what you want to do is you want to figure out what's the conjugate acid. So the conjugate acid is HF, and then you look up the Ka of HF. Okay, so that's in the back of the book. And so now you use this relationship here and to solve for Kb. So Kb is going to equal Kw divided by Ka of the conjugate acid. So this is going to equal 1 to the negative 14 divided by 3.5 to the negative 4. Okay, and so this is going to be the Kb for F minus. Okay, so doing that, that's how you go about getting the Kb value. So we'll get into equilibrium calculations where we're solving for concentrations or constants later on. Okay, so we might start doing those for Wednesday's lesson. Okay, so I'm going to stop there. So again, I'm starting to get some more questions from students. So let's keep that going. So these are the questions you can work on from the textbook. Like I said, I showed you how you can access the textbook if you don't have one at home. You can access it online, but you do need that access code. I've had a couple students send me a message to get that code, but I haven't heard from the rest of you. So I'm assuming you have textbooks. You do need to get access to the textbook for what we're doing here. Again, if you haven't contacted me regarding that, please do so. So have these questions done prior to Wednesday's lesson. And if there's any of these that you're unable to figure out, just let me know, and then I can begin Wednesday's class by going over that. And also, read through the sections of the textbook that we're covering. I'm going to follow it in the exact same order, and if there's anything in the textbook that doesn't make any sense you want clarification on, just ask me about that as well. Okay, so again, let's keep the communication lines open. So have this done for Wednesday. Again, look after yourself. Hopefully things are getting a bit better. Okay, so I'll talk to you on Wednesday. Bye now.